Today we're doing 2.1, we're doing translations. So we kind of covered translations back in chapter 1, but basically a translation is where you take something and you slide it left, right, up, or down, but you preserve both the orientation and the size and shape. So keep that in mind. One term that may be new to some of you is a vector. So it talks about vectors right here. But essentially, vectors are usually drawn as kind of like array here. They look like array, but we don't have points necessarily drawn on them. And vectors have letters, and they have a little one-sided arrow type thing, like a little V arrow thing. And vectors you can think of as rays, except instead of going on forever, they just end at a certain point. Or you could think of them as segments with a direction. So, for instance, this vector here is this length and in this direction in its order to use it. You guys ready to see it? Okay. For vectors, we can, in the coordinate plane at least, we can give them values simply based on the horizontal change and then their vertical change. So this is just like you would a point. The horizontal part is here, the vertical part is here, but with a vector, it's the horizontal change and then the vertical change. Vectors also look different than points. We have to, because there's these two parts and we separate them with a comma, we have to make it clear that we're talking about vectors. In this case, we'll use these little brackets, these 8 corner bracket type things instead of a nice round parenthesis mark. So this vector goes A units to the right and B units up. Obviously, if B was negative or if A was negative, then it would be left or down, respectively. So we could say that the component form of vector PQ, so here's vector PQ, is 5, 3, because it's 5 to the right and 3 up. Another way to think about these vectors is if the starting point is always at the origin, the component form of the vector will be equal, right, the same values as the end point of that vector. So if this is at 0, 0, right, if here's my graph, then this end point of the vector is at 5, 3, right? That only works for if it's starting at the origin. If it's not starting at the origin, it may be different values, but the vector itself will be 5 over and 3 up, no matter where you are. Just be aware that if you translate something to the right or the left, that x value will change appropriately, and if you go up or down, that y value will change appropriately. So be aware of that. We'll do some examples here. This one says, calculate the verticals of the image figure, graph the preimage and the image. So the preimage coordinates are these ones, and then here's the vector that we're going to doodle on. So they predict it, but we're basically going to do the same as before. We're going to write down our coordinates for our pre-image, and then we're going to write down the coordinates for our image. We've seen this sort of thing before with, this is just a specific type of transformation. So in this case, our pre-image coordinates, a little hard to see here, are negative 2, 1, negative 2, 1, that's A, negative 3, negative 2, negative 3, negative 2, they did C for some reason, and then B is at negative 1, negative 2, right, negative 1, negative 2. Then we apply the vector change, so in this case the vector is 4, 6, and remember if the in this case we simply add the values of the vector to the points here, because we're adding 4 and then we're adding 6. So in this case 2, 1 becomes 2, 7, negative 3, negative 2 becomes 1, 4, because we've added 4 and added 6 to the x and y values respectively. So that makes these 3 points here, and then ta-da, we're done. Okay, we'll try another one. Here's our pre-image, 3, 0, 2, negative 2, and 4, negative 2. So they've written them down here. The vector is negative 2, 3. And so this means we're going to go negative 2 units to the right, which means 2 to the left. So boop, boop, boop. We can graph it a little bit here. And then 3 up. 1, 2, 3. So the vector is going to look something like this, right? Just ballpark. In fact, I'll do it here. We'll start here. We'll go 1, 2, and then up 3. 1, 2, 3. So I can just delete it. Watch this. So the vector is going to do something along those lines. It's a little more accurate. I'm going to move that and then erase these. Okay. And then we can use this to kind of test later. So here are original coordinates. The vector is going to move it to the left and then up. The general prediction is, okay, so all of these values are positive for the first value and negative for the second. So that means that they're positive over here and negative for the second, which means that they're in the fourth quadrant. After we apply this vector of -2, 3, we're going to move up in this direction. So we can make a prediction of what quadrant it'll be in. We can be like, oh, maybe it's in quadrant 2 here. We'll see. Oh, 1, sorry. So then we can do these values. We're going to subtract 2 from our x because that's what the vector is. Then we're going to add 3 because that's what our vector is. So x minus 2, y plus 3. So what is 3 minus 2? Hopefully you got 1. What is 0 plus 3? Hopefully you got 3. Similarly, go ahead and fill these ones out real quick. Then I'm going to pause. Hopefully you got those values. And then finally we get to graph it. So I'll do 2 colors here. Let's start with black. I'll do the original points. So 3, 0, 2, -2, 4, -2. I can label them so I know that this is point A, this is point B, this is point C. Cool. And then we can apply our cool vector, or we can just write, well, we'll write down these points. So we're at 1, 3, 1, 3, right here, 0, 1, right there, and then 2, 1, right here. Okay. So this is A prime. This is ugly B prime, and C prime. Yeah, do you see that, Runner?
Yeah.
Do you see the triangles?
Yeah.
Okay, and then we'll see if it matches our vector here. Hooray! A to A prime, B to B prime, and C to C prime all match that vector. So we're pretty sure we did that right. Okay, see if you can do this one. We'll pause it for a sec. Pause.
You're
welcome. Right. So for this guy here, the vector is the same for both. The vector is -4, 1, so that means 4 units to the left, and 1, which means 1 unit up. So 4 units to the left, up 1, 4 units to the left, up 1 for both of these. Should look something like that. Okay, for this one, basically we're working backwards, right? So we're given these values and we have to determine what the vector is. In this case, we can look at our pre-image and we go, oh, here's our pre-image. Here's our image. So we've obviously moved to the right, moved down. So therefore our first value is going to be positive. Our second value will be negative. And we can get a little more specific. Instead of looking at the image as a whole, we can look at a single point. So we can look at a single point. In this one, feel free to just count. You don't have to be super fancy about it, like the book does. But we can just look at point B here, and we can say, okay, well, how far to the right does it go? Well, it goes 1, 2, 3, 4, 5 units to the right. So the first part of our vector is 5. And then how many units down? 1, 2, 3, 4. So it goes 4 units down, so it's -4. So that's where we can come up with that vector. We'll do another one. This one says, draw the vector. I drew it for you. Describe the components. So the horizontal change is, again, we can just count here. We don't have to make it fancy. 1, 2, 3, 4, 5 units to the right. How many units up? 1, 2, 3. So it should be 5, 3. They get theirs by subtraction, but subtraction here is the same thing as counting. They're just subtracting the x values to count that distance. And then subtract the y values to count that distance. The nice thing about the subtraction method is you can do it without the graph present. So that's pretty handy. Okay, go ahead and see if you can do both 7, 8, 9, but also 10, 11, and 12 while you're at it. So pause.
Oh.
Okay, number 7, the component form of a vector that translates horizontally is simply going to have 0 for the second value there. Shh, quiet please. The first part of that component form will be some kind of, shh, if you can't be quiet, you can leave. Will be some kind of value. It doesn't matter what it is. For this one here, you have to refer back to 3a here, but it basically asks for that that vector as -5, 4. Number 9. How are translations along vectors a, -b, and -ab similar, and how are they different? Well, let's take a quick look at it. If I was here in the coordinate plane, and I went a, -b, that means I'm going to the right and then down. I'm going to be like this. If I was -ab, that would mean I'd go left and up. So I'd be going left and up. The same amount I'm going right and down here. Number 10. A translation along vector -2, 7 maps point P to point Q. The coordinates of Q are 4, -1. What are the coordinates of P? So when it says maps point P to point Q, it says that P is the starting point, right? We'll just do a little thing here. This is point P. Don't know what the vector is, but it ends up at point Q. And it gives us the values of point Q, right? So we can algebraically just think, okay, what numbers plus -2 plus what number equals 4, and 7 plus what number equals -1? Well, it's 6 and -8, right? So instead of adding these values, we'd subtract these values from point Q. Uh, 11, a translation along vector AB maps points in quadrant 1 to points in quadrant 3. What can you conclude about A and B? Okay, so here's our, okay, quadrant 1 is over here. And it says it points to quadrant 3. So this is 2, 3. So the only way we can go from 1 to 3 is if both components of that vector are negative. And then finally, how does translating a figure using the formal definition of a translation compared to the previous method of translating a figure? It's the same, more or less. But here we actually have values that we can associate it with instead of just saying a shift left and up and down. We can name a specific vector. Anyway, that's it. Have a good day. Say bye, Renner.
Bye.